Here's a simple harmonic motion kinematics example. We're given that we have a mass, it's oscillating on a spring, and we measured position as a function of time with a motion sensor like in the lab, and we want to answer we can get a whole bunch of information out of this graph, including what the velocity, acceleration, and force graphs look like. And so maybe the first question we would want to answer is, what is the period? And so here is a crest. And here's another crest, so that is one cycle, and so the period is 2 seconds. You can also check it from trough to trough, or from x equals 0 on the way down to x equals 0 on the way down or up, and you're always going to find out it is 2 seconds. Frequency, it's probably easier to read the period and then know that the frequency is 1 over the period, right? And so the answer to the question, what is the frequency, is 1 over the period. In this case, 0.5 hertz. What else could we get? How about the angular frequency? This would be knowing the equation for angular frequency. It's kind of like angular velocity, change in angle over change in time for angular velocity. And so one cycle, 2 pi over the period. And since the period is 1 over the frequency as well, it's also 2 pi times the frequency. And you should know the equation for frequency for a spring mass, 1 over the square root of 2 pi, 1 over 2 pi square root of k over m. And so if I multiply this by 2 pi, I get square root of k over m. And I think the easiest one is 2 pi over the period here. And so we get pi is the angular frequency. What else can we get? How about the amplitude? That's pretty easy. You just read it right off the graph. But the question is it 8 or is it 4? And you should know that it's the distance from the midpoint, and so the amplitude is 4 meters. How about what function are we looking at here? You should know that if it starts off at maximum, positive, that is a cosine. And so we can write the equation for x as a function of time. We have to have amplitude out in front because cosine can only get as big as 1, and our amplitude's 4, so we need to multiply by that. And then here in the argument, we have the angular frequency times the time. This ensures that x goes through one cycle in one period. If you put in 2 pi over the period, you'll see that's the case. And so we figured out the amplitude and the angular frequency, so we know that's the equation for x as a function of time, and that's what's graphed here. How about velocity? What function would the equation for velocity be? A couple ways to get that. You can imagine a spring mass bobbing up and down, and we know the velocity at this point, and this point is all 0. And so we could mark those. And then we know at x equals 0, we have maximum speed. The question is, are we on the way up or are we on the way down? And if we're on the way down, that is negative. And so we're here. We don't really know where the maximum is yet, but somewhere around there. And then here, we're on our way up, and so that would be positive velocity. And so we can see we have a negative sign, right? A sign would go up starting. This is a negative sign. You can also get it from the slope, right? And so the slope at these points, draw a tangent. Slope is 0, 0 velocity. Here the slope is negative. So we had negative, and it's the steepest right here. And here the slope is positive, and so we have positive velocity, and it is the steepest right there. And those of you in calculus know it's the derivative, but you should be able to follow this analysis as well. And so we have negative sign for the function, but we want to know what the maximum is, so we could sketch that. How do we get the maximum velocity? Conservation of energy. Simple harmonic motion, the energy doesn't change, so the energy at x equal x max is the energy, well, anywhere else, we're interested in x equals 0 when we're going the fastest. And so at x equal x max, it's all potential, elastic potential, and at x equals 0, it's all kinetic. And so we can solve for V maximum, and we get x maximum times the square root of k over m, and we don't have k. You could solve for it since we're given the mass here, but we also know square root of k over m is the angular frequency. And so this also is the maximum velocity. Make sure you can derive this, though. It's okay to just memorize that, but make sure you can go through this. And so the velocity has got to be negative sine omega t, and we need the amplitude of the velocity out in front, v maximum, and so we know what all those are, and so we have negative 4 pi, pi times 4 sine pi t. And so if we were to graph that, well, if we graph that, 4 pi is about negative 12.6, and so it's going to look like that. So I wasn't too far off here. If I erase it, I'm exactly on. And so our next goal is to figure out what acceleration and then force looks like. So we're going to get rid of all this stuff here. So if you want to take notes, pause it here. Here we go. Bye-bye. And so now we're looking at acceleration. What function would we have for acceleration? That might be a little tougher to look at the velocity unless you think of slope. Let's go back up here. The spring is bobbing up and down, and I know that when I'm at x equals 0, that's called the equilibrium position. That means the sum of the forces is 0, and so the acceleration has to be 0 at those points. And at this point, the spring is stretched the most, but it's stretched this way, the force is down, and here the force is the most, but it's up. And so if the force is up, I have a positive force, I have a positive acceleration, and so that would be there, and this would be down here. We don't know what the maximum is, but we do know enough to sketch our graph, and we have a negative cosine. Also think slope. The slope of a tangent at those points would be 0, so the acceleration is 0, and the slope here is maximum at that point, and it's negative, so I have my biggest negative acceleration there, and then the slope here is positive, so I have the biggest acceleration there. We didn't do this one, but that locates me there as well. And so negative cosine. So the next question is, what is that maximum acceleration? We get that from Newton's second law. Acceleration is the force over the mass. For a spring mass system, the force is kx. And if I want the biggest force, I want k times the amplitude x max. And if you remember, omega is the square root of k over m. So k over m has got to be omega squared. And so again, this is handy to know, but make sure you know Newton's laws here and can apply this. This is a simple Newton's laws application. Should be able to do that. And so now we can write the equation for acceleration. Oops, mistake here. That should be a max. That's what I get for cutting and pasting. And so the acceleration is negative cosine, omega t here, and a max out in front. And so a max we found out was omega squared x max, so pi squared times 4. If you remember from before, omega was pi for this problem, right? And there it is right there. And so that's the acceleration equation. If you multiply this out, you get about negative 39.5. So if we graph that, hey, we weren't too far off. And if I erase it, we're exactly on. And now all we need is a force. And this is a little easier. What function would we use? Well, F equals ma, right? These two are vectors. They've got to be in the same direction. All we're doing is multiplying a scalar mass times our acceleration equation. If the mass is 1 kilogram, the equation would look just the same, just different units, right? It'd be in newtons. And so it's got to be the same function. And so negative cosine, negative cosine. We don't have to go through the slope and stuff. You could look at that, but we did it for acceleration. So what's the maximum force? You could use what we have up here, kx max. Or since we already have the maximum acceleration, it's just ma max, and so I multiply m times omega squared x max. And so this would be the general form, and putting in our numbers. The mass, if you remember, was given as a 0.5 kilogram, and so force is this, and if we graph it, it looks just like it. So look at some patterns here. When you go from position to velocity, it's shifted, right? And so it shifts back. This peak here got shifted over. This trough here got shifted over. If you compare position to acceleration, they're the same except a mirror image, right? You have a trough, you have a crest, and then force and acceleration are the same. So some people start to notice patterns. Let's take a look at a summary of this, and we'll see what we notice. And so these were the results we got. And so some people notice, hey, if I start with a cosine, whether it's x or v or acceleration, whatever I'm doing, and I go down, I take the derivative or slope, I get a negative sign. And if you have a sine and you take the derivative, you go down the slope, you get a cosine and the sign doesn't change. And so then if I have a negative cosine, what do you think you would get next? Well, it would be a sine, and then the sign would change. It'd be a positive sign. And that just keeps going. So if you want to practice, start with something and just see what happens. The other thing that happens is we saw the angular frequency got multiplied out in front. Remember, Vmax was omega Xmax, and then, oh, there's that mistake there. And that's omega squared Xmax. So look for these patterns, but also make sure you can go through step by step. How about a practice example for you? Can you determine the equations for velocity, acceleration, and force, and x as well for this example here? And so I'm going to give you the answer in a little bit. Notice this is different than the previous example. Mass is still 0.5. So pause the video, see if you can work through all that. Okay, here comes the answer. No cheating. I said no cheating. Pause. Here they come. There we go. And so if you're able to do that, you have mastered this skill.